first thing we're going to define is the rule of principal square roots. And what is a square root? So here's our definition. I've written it out ahead of time. We're going to define when you see a equals square root b, we're just using those letters because they're in the alphabet, that's going to be defined as the positive solution to the equation a squared equals b. And there's a couple things we want to take apart here. What this is basically saying is that square roots and squaring are opposite operations, but also there's some technicality with the positive solution situation. So the idea is in pre-calculus, we want to think of things as functions, and functions only have one answer or one output. And so situations with multiple answers, when there's a single thing written on the page, are actually confusing and bad for us. So that's different than actually solving the equation y squared equals x. For example, you've been trained for years and years in all of your algebra classes very well that when you solve this equation, you can take the square root of both sides, and you get y is equal to the square root of x. However, when you do that and you take the square root, you've been trained to add a plus or minus sign because you're solving the equation, you're finding the solutions to such an equation. So, a more concrete example is that x squared equals 49 is an equation you might solve. You solve it by taking the square root or just looking at it and identifying the solutions. There are two numbers that when you square them, you get 49, 7, and minus 7. However, when you see square root 49 written out, and this is in operation for the entire year, everywhere in our textbook and pretty much everywhere from here on out. So it's a forever rule. When you see square root of 49, what that's referring to is the positive version of that root, the positive one only. So don't, like what people think is they say, oh, a square root, and they sort of mentally put a plus or minus sign there. That's wrong. When you see the positive version of the root, or you see the root without anything, that's the positive version, positive 7. If I, the author of a textbook or a worksheet or whatever, want you to think about the negative version, the negative root, I, the author, need to write negative root 49, and only will that equal negative 7. And it's true with roots that don't reduce also. So square root of 2 doesn't reduce. It's better to just write it as square root of 2. But you should know that that's the positive square root of 2 when it's written there, positive 1.4, whatever. If I want you to think about the negative number 1.4, whatever, I need to write negative square root of 2. And so that's the rule, and that's called the principal square root. Or like the principal root rule, and the positive root is called the principal square root. But if you're talking about in class and you say, hey, why is there no plus or minus here? We'll probably just say, because of the principal root rule. And this is what we're talking about. So it's because we're not solving an equation. We're looking at a single specific number that has been defined by us. We've made a choice that when we see that symbol, that's just going to be the positive version. And if the author puts a root there but wants you to think about both, it's their job to put the plus or minus. Now, that doesn't excuse you. I'm going to go back here. Does not excuse you when you're solving an equation from including plus minus. That's still true, just to be clear. It's just when you see a root written on the page. All right, we're coming to our second tricky topic, and I'm, again, just trying to get these out of the way before we go into examples because, we're going to front load with the weird stuff. And the weird stuff here is expressions like this, the square root of x squared. Now, you've maybe learned or maybe seen before this idea that the square root of x squared, a square root, and a square cancel out, and the square root of x squared is always just equal to x. Those reduce out, and that's simple. While that's true, sometimes it's not always true. And in math, of course, we don't like things that are only true sometimes. We want things to be true all the time. So I want to explore this idea a little bit more. When would this be true and when would this be false? Well, here's what I want to think about. I'm going to write my square root of x squared again, but I want you to think about the principal square root rule. This root is on the page. It's written right there. It's like, in part of an expression, in an equation that you've already gotten. So when you see it, the principal root rule means I'll say the PRR, means that this is the positive version. However, x could be positive or it could be negative. And we're not sure. And there's nothing in the problem that says, at least yet, whether that x is positive or negative. So let's think about two different situations. Why don't we do an example? I want to do the square root of 5 squared. Okay, the square root of positive 5 squared is equal to the square root of 25. The square root that's written on the page is always the positive one, so the answer here is positive 5. So in this case, it appeared that the square root of x squared equaled x. However, what if I plug in negative 5? Negative 5 to the second power is 25. The square root that's written is assumed to be the positive root because of the principal root agreement, we'll say, assumption. So this is also equal to 5. So in this case, the square root of x squared simplified to, it started at negative 5 and became positive 5. So if we're abstracting that to writing about x, I'd write that this is equal to opposite x. Not that x is negative. It actually means that this is positive, because x was negative, and so negative of negative x is a positive number. And that's interesting. We have a case-wise situation where the rules are different depending on whether x is positive or x is negative. But wait, we already had something, if you think back just a video ago, that did this exact same thing. Remember our definition of absolute value x. This is so cool. I love this. Was equal to x if x is greater than or equal to 0, and opposite x if x is less than 0. Well, guess what? Square root of x squared has the exact same behavior. And if in math, if two things have the same behavior for all x values, they're the same. So here's what we're going to write. The square root of x squared is equal to absolute value of x. And that's always true. Now there's a couple complications, and we're going to get to those maybe in a little bit. Here's one. I'll put one complication right here that shows up a lot. We'll just say star complication. This is only necessary if we know that x could be positive or negative. So, in the directions, for a lot of problems, there's a statement, something like x is greater than 0, or assume that x is greater than 0. Well, if that's true, then I'm doing this, and in the problem there's a square root of x squared. I would say, okay, square root of x squared is equal to the absolute value of x, because Mr. X said it's always true. However, because x is greater than 0, this can simplify further into just x, because if x is greater than 0, absolute value of x simplifies to x. So there is always actually an absolute value there, but when you look at your answer sheets, it's not always going to be part of the final answer, because sometimes that absolute value will simplify back out. And that can be really confusing because it can depend on the problem you're doing. It can also depend on the just literal directions in the problem about what the domain on x is, if it's that assumption or not. We are going to see this later on in the video in a couple sets of examples, but I want to say a couple words more about this right now, and the words are, don't worry too much about this. It's important, and it is true, and you need to know this property, and when it applies and when it doesn't. But what I see in Math 4 so often is students focus on this property, and they spend 95% of their studying energy learning this property when they haven't learned any of the other fundamentals. And when the quiz time comes, They get the first 4.5 problems wrong, and they're all ready to answer the absolute value part, but every other part is wrong. So that's not great, obviously. If you want a sports analogy, it's like the person playing basketball that only practices throwing from the half-court line and never practices any other part of the game. So make sure that you're practicing all parts of the game, including this important rule, but don't focus all of your energy on this rule, even though I know that you want to. All right, so we're now going to get into a little more concrete space where we're dealing with some actual numbers for a while. There are two properties, or there's one important property of roots and one non-property, and I've written two potential properties here. One of these is true and one of these is false. Maybe pause the video, think about it for a second if you're not sure. All right, and I will tell you that the first property is false. It's falsy, false, false, false. That is never, ever true. So when you have two roots like this, and you don't have like bases, you can't add them up and make, for example, square root of 5. That does not work. However, when you have roots and you are multiplying them, you can combine them. So we might write that root 2 times root 3 is the same as the root of 2 times 3, which is the same as the root of 6. That is true. Just be really careful with the addition property because sometimes we get really excited and wish that we could do it, but we can't. There's one caveat to that. You can add roots with like bases, but you don't actually add the bases. So for example, 2 root 3 plus 4 root 3 can be simplified to 6 root 3. But notice, it's kind of like adding exponents or variables even. That just stays as a single object, and you're just saying I have 2 apples plus 4 apples, and I have 6 apples. So that is legal, but that's different than this step, which is illegal. You've probably seen problems like this before. Using the product property, it might ask us to reduce the square root of 500. The way that this works is you're going to use that product property to turn this square root into roots of other numbers you know. So for example, 500 is 50 times 10. I'm kind of doing this in maybe not the obvious way because I want to show something off. This is the square root of 50 times 10. That can be turned into the square root of 2 times 25 times 10. That could be turned into the square root of 2 times 25 times 2 times 5. That could be turned into the square root. So you can use the product property multiple times underneath the root. 2 times 2 times 25 times 5. Why would I do that? Well, because 2 times 2 is 4. And then you could split the root back up. So, when you have, we looked at the property forwards, but it's also true backwards that square root of 6 can be written as square root of 2 times square root of 3. And why would you do that? Well, you do it here because this can be written as the square root of 4 times the square root of 25 times the square root of 5, which is the same as 2 times 5 times the square root of 5, which is 10 root 5. Now I just did a lot of steps, and you probably won't do all those steps when you're reducing roots, but mathematically, that's what's going on here. What you've maybe seen, and actually how I like to do these, is by taking the number under the root and just making a factor tree. 500, just pick any factors you want. How about, I'm going to do different factors. How about 5 and 100? Now, when you see a factor that's prime, you can stop. And when you see a factor that's a perfect square, you can also stop. That's a way to break it up. So that would tell me that I could write square root 500 as square root 5 square root 100, which would be 10 root 5. But you can also keep going. Say, oh, I forgot 100 is a perfect square. It's been a really long day, guys. I don't know my perfect squares. 100, I don't know. That's 10 times 10. That's 2 times 5 times 2 times 5. If you get all the way down to all the prime factors in your factor tree, what you can do is look for pairs. And again, this is kind of the exhausting way. It's easier to look for perfect squares, but if you get all the way down to the prime factors, I see a pair of 2s, I see a pair of 5s, and I see left over 1 5 that's not in the pair. And I feel like sometimes I get students that say, oh yeah, I learned all about the factor trees, and then my teacher said, oh, and the 2s and 2s are friends, and they hold hands and walk outside of the square root forever and ever and have fun. That's ridiculous. That's not what happens. What's happening is it's the product property of square roots. So, you can use a factor tree, but also it's important to know mathematically why this is true and what's going on. They don't just walk outside of the square root because square roots are fun and magical. They walk outside of the square root because they're a perfect square underneath the root. One more thing on factor trees. A lot of folks just get stuck staring at factor trees. Say I asked you to do, we'll do 500 again. And say, I don't know any factors in that number. It's too big. Like, my brain hurts. I say to you, it doesn't matter if you pick the right factors or the perfect factors. Just pick anything. 500 is even. Divide that thing by 2. Oh, gosh, 250 is even. Divide that thing by 2. And at some point, oh, that ends in 5. Let's divide it by 5. And so you don't have to go to the smart factors right away. Literally any factors will work. Divide by 2, divide by 3, divide by 5. That's the best way to make these factor trees. Here's an example that's a little more exciting. Square root of 4x cubed. Now let's take a look at this. I don't see any restrictions on x telling me if x is positive or negative. So again, sometimes there's directions about whether x is greater than 0 or less than 0. I don't see any restrictions there. X could be negative or positive. So I could split this up into the square root of 4 times the square root of x cubed. Square root of 4 is going to reduce to 2. That I know. X cubed, though, I need to split that up into 2 things. Remember what x cubed is. That's x squared times x. So we'll do this in a bunch of steps. So that means that this could be the square root of x squared times the square root of x. And this is what you do when you have like kind of a mismatched root and power. Okay. Now wait. I'm going to have a root x, I'm going to have a 2. Remember what we said about root x squared, though. Since we don't know if x is positive or negative, but we do know that this positive root of a perfect square will be always positive, we actually have to write absolute value x. So in this case, the final answer would be something like 2 absolute x root x. And that's something to really watch out for whenever you're doing, I think I've written it down somewhere here, whenever you're doing a square root of an x squared, you're always going to have that absolute value. All right, let's do another one. But I want to look at this a little bit first. I want to look at this a little bit first. I notice right away that this is not simplified yet. And I notice I have a square root of x. Now, it is illegal to take the square root of a negative number, which means that for this to be a legal expression as written, x has to be greater than or equal to 0 implicitly. That is, it's not stated directly in the problem, but it's there based on the rules of roots. And that's going to be important when we get into the absolute value thing later. Okay, so here I'm going to put a star by this idea, but now we'll just simplify this down. This is the square root of 5 times 10 times x, which is the same as the square root of 50x squared. 50, so sometimes you can just make your factor tree right inside, is 25 times 2. So when you square root both of those, that's going to be 5 root 2 times the square root of x squared. Now watch real carefully here. Square root of x squared is equal to the absolute value of x. Always. Except because x is greater than 0 or equal to, absolute value of x simplifies to just x. So this answer is going to simplify to 5 root 2 just x, no absolute value. And again, this is why people get so hung up on the absolute values. Sometimes it's there, sometimes it's not, and it's kind of subtle about when it is and when it's not there. By the way, also this could be written as 5x root 2, or I guess x 5 root 2. Probably most often you'll see it here. Usually roots are written at the end because you want to be clear what is and isn't under the root. But it's weird to write the x first. So usually the x gets sandwiched in the middle. But you can also write it as 5 root 2x, or even, if you really want to be clear, 5 root 2 parentheses x to say, hey, make sure the x is not underneath the root. Okay, let's take a break from absolute value stuff and go into fractions. So the rule about products is also true for division. So when I see the big giant square root of 8 over 49, you can immediately interpret that as the square root of 8 over the square root of 49. That can simplify further to 2 root 2, that's 8. That's a 2. Over root 49, which is 7. And again, none of these are plus or minus because the root was written on the page the whole time. And then 2 root 2 over 7 is as reduced as it gets. You don't have to do anything further with that. One thing people sometimes shows up that's helpful is say that you have a square root of 50. Yeah, that's a good one. Over square root of 2. Now, what some people will do is say, you can't have a root on the bottom. Let me rationalize this and go to all this. We're going to do rationalizing next. But here's the smart way to do it. Use this rule in reverse. So write this as big square root of 50 over 2, which is the same as square root of 25, which is 5, which is how the other one would simplify if you did some goofy rationalizing nonsense. And this is the one that folks always say, oh my gosh, I didn't know that was a rule. Well, it is, so happy birthday. I've given you a nice new rule to use. And our last topic about square roots is rationalizing roots. So there is a myth in math that this situation with a root on the bottom is illegal. That somehow that's not a real number, or it's bad in some way. All of that is wrong. If you think that, or you've been told that, you've been lied to, and I'm sorry on behalf of math teachers everywhere for lying to you for so long. It's not illegal. It is, we'll say, at worst, impolite. And, there's some really good reasons for saying that we used to say you can't have a root on the bottom. I think the main one is that we didn't used to have handy-dandy calculators that we could pull up at any instant. And when you wanted to do a square root, you actually had to go to a literal book of square roots. And in that literal book, they didn't have denominators. They only had numerators because it's possible to switch them around. And you don't want to end up dividing by something that has infinite length. You'd much rather do division the other way if you think about how long division actually works. So that's why we used to say rationalizing was illegal. It's never been illegal, but it's been impolite. But it is an important trick because in Math 4 and calculus and further on, the most important thing is not a specific rule. It's about you being able to manipulate expressions in any way you want them. So what can you do to manipulate an expression like this? Well, there's a couple problems. One, it's not an equation, right? If I said this is equal to y, you could multiply both sides by something. It's not an equation. There are no both sides. You can't do any both sides operations. So I couldn't add 1 to both sides because there's another side. But what you can do instead, the only thing you can do is multiply by 1. Now I'm not going to multiply by 1. Why don't I multiply by 1 over 1? That's the same thing. Well, I'm not going to multiply by that. What I really want to multiply by is something that will make this root reduce. So I'm going to pick a fraction that is equal to 1, but will reduce the root in the denominator. And that's my goal. That's what I'm choosing to multiply by. So what happens here? Let's do the calculation. The top becomes 3 root 2. The bottom, root 2 and root 2, that becomes 2. And you end up with 3 root 2 over 2, which 3 and 2 are relatively prime, so that simplifies, and that's the answer. That's rationalizing. It shows up a lot. I'm not going to require you to do it like in general. There will be some problems that ask you to rationalize to show you know how. But like when we get into trig and you're doing right triangles and stuff, I do accept things like 1 over root 2 later on in the year. Here's another example of rationalizing, and I do need you to know how to do this because when you rationalize this, it actually becomes a lot nicer. So again, we have a root on the bottom, not great. Let me try what I tried before, which would be multiplying by, I guess, root 3 over root 3, a version of 1 that seems like it would cancel out that root. Okay, on the top, I'll get 4 root 3, and that's okay. I can have that. But on the bottom, you have to treat that as if it's distributed to both terms, and just root 3 will give you 1 root 3 minus 3 times root 3 is 3. So I end up with 1 root 3 minus 3. Now some people might say, well, Mr. Eck, doesn't... Oh, I went too far. Mr. Eck, doesn't this cancel out? No, it doesn't. It's not in both terms. It's not factored out. You're still missing a root out of that second term. Ooh. So this actually doesn't work at all. You need a better strategy. And I'll give you the strategy first, and then I'll show you the reason why. What you're going to have to do is multiply by this thing that's called the conjugate of the denominator. The conjugate is the same numbers, but with a flipped sign in the middle. Flipped sign in the middle. And let's do the multiplication, and we'll see what actually happens when you multiply by that conjugate. So multiply the top, you distribute the 4, it becomes 4 plus 4 root 3. That's standard. Let's do the bottom. Now I'm gonna reserve this space for my answer, and I'll do some scratch work down here. So I get 1 times 1, I get 1. I get 1 plus root 3, I get 1 plus 1 root 3. I'm going to do this minus 1 times root 3, so I get minus 1 root 3. And then I do minus root 3. Remember that this negative is attached to the root 3, times root 3, and I get minus 3. Well, guess what? These middle pieces have canceled out, and the root is gone, and all this is 1 minus 3, which is negative 2. So the entire denominator, has become negative 2. That's beautiful. Look how easy that was. Now look what we can do. So we said before there was some illegal canceling, but what is legal is to say, 4 and 4 are both divisible by 2, or maybe negative 2, and so this can simplify to negative 2 minus 2 root 3. Again, both signs flip because of the negative, and the 2 divides out of both 4s. Look how simple that is. And this is why I might ask you to rationalize it. Look at the complicated, how complicated the original was. Fraction, subtraction. Look how nicely the simplified version is. That's why you do this. And I'll close with just a little more on conjugates. This is a slide straight from your book. You can have conjugates with multiple roots. Often it just has 1. But so we had 1 plus root 3 and 1 minus root 3. But you can have multiple roots. But the way that this always simplifies is that what we call the middle terms always cancel out. And you always end up with first term squared minus second term squared. But when the terms are roots, it ends up being a and b. I also think about it without the roots. This multiplying pattern. A plus, I'm going to use different letters. We'll say x plus y times x minus y will always equal, I'll do the scratch work, x squared minus, plus xy minus xy minus y squared. So you get x squared minus y squared. Always true. Now when some of those are roots, that's why there's not a squared on the roots. But that's the general factoring pattern. It's called difference of squares. And if I'm being honest, it's probably the most important factoring pattern in all of Math 4. So if you're not really familiar with that, I suggest you take a second and multiply that out and really explore that a little bit more. But it is the factoring pattern that lets a lot of things happen, including rationalizing goofy denominators like this one. All right, we're going to cut it here. Thank you guys for watching. I know this has been a long one, but roots are really important. They never really leave, and a lot of people have a lot of good questions about roots every single year. So, let me know what questions you have. I'll see you guys in the next video.